Everyone, CocoaButterCoder here, aka Coco, and welcome back to another Cypher Saturday video. This can be considered kind of like a part two to my last frequency analysis video. Um, and I say kind of because it's probably 80% independent. Like they're both using frequency analysis, so there's overlap there, but the methods in which to do so are not the same at all. And I'm actually excited because if you saw that video that I posted earlier, I said that the first approach that I took in that video didn't really go the way that I planned. It seemed like there'd be too many rules that I would have to code, and it just didn't seem like the best approach to go about it. But this method was supposed to have better results, but I wasn't really getting those results, so it worked maybe better, but not as well either. But I realized the mistake that I made, so I'm excited to say that it works the way that it's intended now. And with that being said, we can jump right into it. So the difference between the last one and this one is the way that we decide what is English and what isn't. So in the first frequency analysis video, we count the frequency of letters and try to apply that to our ciphertext. And it's not always a one-to-one relationship. If K is the most common letter in the ciphertext, it's not necessarily E, especially depending on the size of the ciphertext, the context of the ciphertext, stuff like that. And so this method is using something called quadgram statistics. And instead of looking at letters and the frequency that they occur, and in the first uh, video I did, I also was looking at the frequency of certain words. So, like looking for what was probably the word the in a ciphertext, and then applying frequency analysis on that. And so this is applying frequency analysis kind of like words, but is focusing on something called quadgrams. So a word is just, some series of letters that has meaning, but a quadgram is just a series of letters. And there are trigrams, bigrams, unigrams. In general, they're just called n-grams, but we're focusing specifically on quadgrams. We could do frequency analysis using trigrams or quintgrams, but this article is using quadgrams, and all of this video is based on this article by Practical Cryptography, Quadgram Statistics, and then there should be another one here. Did I go back? Yeah, cryptanalysis of the simple substitution ciphers, which for our case is just a monoalphabetic substitution cipher. Um, And so the way that this quadgram statistics work, in the same way that we can go through a text, count up all the letters, and apply a frequency analysis of an English text, we can go through a text and find all of the blocks of four letters and apply, tally those up, create a dictionary the same way that we did, and then use that to apply frequency analysis on a plain text. So for example, if I go into Visual Studio Code, I have something called like this is a message. Now, this would be a plain text message, but if we got rid of all the space and say there was some punctuation or something, we could get rid of that too. And now we have one single string that has multiple quadgrams, such as this, such as HISI, such as MES, ESSA. Those are all quadgrams. It doesn't wrap around, so GETH isn't a quadgram. Um, but then we can compare that to, the same way that the code book had like a list of uh, quadgram free or not quadgram but letter frequencies. There's a constructed list of quadgram frequencies for English text, and we can use that and compare it to see how close our attempted plain text is to English. Now, the one thing I will say, and I said this in the last frequency analysis video, I don't know how these frequency tables are constructed. So the one on Wikipedia and the one in the code book by Simon Singh, I don't know what the source is. I don't know if they were looking at articles, scientific journals, nonfiction, fiction, some amalgam, um, like if it was weighted one way more than another, and the same thing with this quadgram. So I'm not using the code here. I just kind of read the article and was like, okay, I think I can do that. And then just coded it myself. But there's a file here called English Quadgrams.txt that I am using. And it has a bunch of quadgrams and their frequencies, like their tendencies in English. I don't know exactly where that's coming from, um, but I am using it for this particular video. So you just like I'm not a big fan of that whole black box kind of like I don't know what the source of it is, but that's the best that we can work with. And I think that's enough information going into this to then just start coding. So I have something called quadgram analysis, and we're just going to do our usual print statement of what is your ciphertext. And so we have a variable ciphertext equal the input, and then we'll just upper that. Just because of that convention I've been keeping, that ciphertext is uppercase and plain text is lowercase. And so we'll print out our ciphertext. Was it? Oh, what happened? Why did it do that? That doesn't matter. Okay, this is message, and we get this is a message, all uppercase. Okay. Um, so the first thing that we can do is then, I guess we can encrypt this. So we can use a random cipher key, um, or we don't have to encrypt it because we're already uh, passing a ciphertext, not plain text. So instead, we can just assemble a frequency table of our quadgrams. So this is the file English quadgrams. It has like hundreds of thousands of lines with all of these frequencies of quadgrams. Like I said, I'm not sure, you know, what text this is pulled from, you know, what sources, but this is what we have to work with. So we're going to open up the file. So we're going to have quadgrams text equals open, and then English quadgrams.txt, and then I'm just going to close it before I forget. So in between, we need a dictionary for our frequency table. So we can do quadgrams frequencies equals an empty dictionary. And I'm actually going to put this just ahead of this one. It doesn't make any real difference, but for structure, I'm going to do that. So we're going to open this, and then we need to return the lines. So we'll do quadgrams text lines equals quadgrams text dot read lines, and this will return each of these lines as a string, and that's something that we can parse and then put into our frequency table. So then for quadgram text line and quadgram text line, so with an S, we're just going to put inside of our frequencies our text line at place. Oh wait, we have to split the line first. So for every line we have to split it. So we'll do, just get rid of this part. So line is going to be equal to text line dot split, and we're just going to split it according to the space because each one is just 4 letters and then a space, and then it does end in a new character, even though, like, you know, it ends at this number. It's saved as a new character, so we need to get rid of that. You can actually see that if we do print. of our quadgram text line. So now we can get rid of some of this, these spaces. But this is a message, and I'm gonna just stop it. Each one ends with a new line character, so that's just something that we have to be conscious of. So we're gonna add each of these um, lines to the dictionary. So quad frequencies at our text line at 0. So that's just our quadgram. That's going to be the key. And then it's going to be equal to whatever we have um, for the second item that was split, just not including the new line character. So that's going to be quad text line at 1. And then we can split that. So everything but the last character. So I think we can just do -1. And now if we print out our frequencies, we should get, this is a message. Yep, we get a quadgram and then just a number. And then the only thing is this number is still a string, so we just have to convert this to an int. Run it again. I'm gonna just do test this time. And now we have our quadgram and then some value. Okay, so now we have the same list that we had here, or the same information, but it's a lot more workable. We also need to calculate how many total quadgrams are, because the way the quadgram statistics work is basically you have some text. So say in this case we have attack. Attack has 3 quadgrams: ATTA, TTAC, and then TACK. And so we take each quadgram that's in attack and then multiply them together. And we're actually multiplying the probability of that quadgram. So here, let's find ATTA. It has this value, and this is the number of occurrences, but the probability would be this value divided by all of the total occurrences. Um, and then we multiply that for each of the quadgrams to determine how likely it is to be an English text. And so that's pretty easy because Python has a built-in um, sum method, so we can do total quadgrams equals the sum of quad frequencies dot values. I'm just going to print that out. It should start with a 4 if I remember correctly. So it doesn't matter what this is. Yep, okay, that's the right number. So get rid of this. Okay, so the next thing that we've done, so we have this in a workable form. We have our total number of quadgrams. We can actually start calculating the probability. Now the thing about the way this quadgram statistics works, we're doing a probability, but apparently there's an issue where, you know, each of these numbers is going to be between 0 and 1. That's how probabilities work. You're taking some number and dividing it by another number that's likely to be bigger. So it's going to usually be less than 1, and multiplying all of these numbers less than 1, especially when they can be significantly less than 1, 0.00, whatever, multiplying them together makes a smaller and smaller number. So you risk something called like numerical underflow. So instead of multiplying them together, you take the log of each of these, and because of the rules of logarithms, multiplication is just another way, or multiplication can be substituted by addition. So you avoid that numerical underflow problem. So first, we're just going to take the probability. And so we have our quadgrams, we have our total quadgrams. We're going to do 4 index in range of ciphertext. And we need the length of the ciphertext minus 3. So this minus 3 is coming from, say we have a 4-letter word like 4. 4 is 4 letters, so it only has one quadgram. So the only index we need to start at is 4, or 0, sorry. This is 4, but the index is 0. If this was like forever, we have 1, 2, 3, and 4. So it's 7 letters long, and there are 4 quadrants. So there's this pattern of taking the length and then subtracting 3 to get the final index that you need. And so we're just going to go length of the ciphertext minus 3. And we're going to say probability equals whatever our quadgram frequency returns of that particular segment. So ciphertext of index to, so if this is 0, 1, 2, 3, we want to add 4. So index plus 4, and then divided by our total quadgrams. Then we can print out our probability just to see what it is. So if I do something like forever, these are the probabilities of each quadgram being in English, or the probability of each quadgram occurring in the English language. So we've calculated our probability, and we want to take the log of this. So log probability is just going to equal math.log of our probability. And we need to import math. So import math. Okay, so we can get our log probability. And the whole idea, this is Quadgram statistics. And this article is actually called Quadgram statistics as a fitness measure. So we need to add all of these together. So fitness equals 0, and then fitness plus equals our log probability. And now if we printed our log probability, of forever, for example, we get some number like -7. So this, like, by itself doesn't really have a lot of context. You know, what are we comparing that -7 to? But the way we're going to do this is we're going to calculate the worst case scenario fitness for any given ciphertext, and then after that, we're going to apply just some random cipher key to it, and then try to decrypt using that cipher key, calculate the fitness again. If the fitness is better, then we substitute the old fitness score for the new fitness score. We save whatever this cipher is, and then we just tweak it slightly to try to make it better. So we can do something like, we need a cipher key. So we have our total quadgrams. We'll do like cipher key, and I'm just going to import random and string because I know that I'll need them. So cipher key is going to be the list of string dot, I guess ASCII uppercase is fine. So this takes A through Z as a single string, and then just converts it into a list so that each letter is its own item. Then we're going to use random to shuffle it. So random.shuffle cipher key, and that shuffles it in place. And then I'm just going to join it back together. So cipher key equals dot join cipher key. Okay, so now we have our cipher key. We need to calculate the worst case scenario fitness. So best fitness, and I'm calling it best because this is where we're going to store our top fitness. But before we apply our plain text, we want it to be the worst so that the first decryption is automatically better. So best fitness is going to be equal to 0. And then we're just going to copy this. So for in this range, probability is instead of this, it's just going to equal 0.1 divided by our total quadgrams. And this, the reason for this is that technically the worst case scenario would be 0, just like this, this particular 4-letter sequence doesn't occur usually at all, like in English. But calculating a probability of 0 is fine. But because we're taking the log to prevent some numerical underflow, I hope I said underflow the first time and not overflow, but to prevent a numerical underflow, we can't do probabilities of 0 because log of 0 doesn't exist. So I just took the lowest one in this list is just 1. So I just took a value lower than 1, 0.1. I could have done like 0.99 or something like that. It was just an arbitrary 0.1 as the worst case scenario, and just applied that for every quadgram unit in a ciphertext. And that we add all that into our best fitness once we take the log of it. And then that's going to be our worst case scenario. So when we do it again here, after we apply our plain text, that'll be our best case scenario. Yeah, okay. So then plain text, it's just going to equal an empty string. So we need to decrypt this. So for character in, we also need to get rid of anything in here in our ciphertext that isn't a space or punctuation, or anything in our ciphertext that isn't a letter. So let's import our regex module as well, and just do ciphertext equals re.sub, and that returns. So we need a pattern. The pattern is just going to be anything that's not an uppercase letter. And then we can substitute that with the empty string, and then we have to pass ciphertext. Okay. So we can now just do for character in ciphertext, plain text plus equals our cipher key at the location of whatever our, so if we have a plain text, like if we were encrypting this, we have a plain text alphabet, just A through Z, and then underneath that our cipher key. So we would find, A, and say what position, or find like K, what position is K at, and then find the corresponding position in our cipher key. So in the same way for decryption, we have our cipher key, and then we find Q, and we find what position Q is at, and then we say what corresponding position or index is this in the plain text. So we have our cipher key. We need to find out like the ord of our character. Since this is uh, all uppercase, we can do ord of character minus ord of A. So say we have Q, I guess QB. Yeah, I think this is how I want to do it. So if we have like cipher key, it's just like YTF, YT, oh my gosh, YTF, etc. Right? We find out where the so let's say Y would be at position 0. So we would actually need the index of Y. Yeah. So instead we're going to do cipher key dot index of our character, and that returns whatever character position this is at. So in the case of Y, which should correspond to A, like if this was ABC underneath. So this is in position 0. A is also in position 0. So if, all right, get out. If the character was Y, that's a position of 0. And we're going to add that, or add to that uppercase A. And that'll return, you know, in this case A, but say if we had T, this is position 1. So 1 plus uppercase A, the Unicode version of that is 97, so 98, and that translates to B. And then we can just do all of this converted to a character, character of this. So let's do print our plain text just to see what we get. And I'm going to use the ciphertext that was used here. Wait. So yeah, this ciphertext is really dumb though, because it has new line characters at the end. So I got to get rid of that. You could probably code something just to like get rid of that. I don't feel like it. I'm more so just mad that this exists in the first place, especially because this guy did it in Python, so he feel like he should know. But whatever. And this again. Oops, got to get rid of this stuff. And this again. And okay, so we come into our first problem on line 36. It's saying that it doesn't know, like it couldn't find a particular cipher or a particular quadgram. So we need to do if, now we can switch this to plain text. So I'm also going to do Quadgram because I think I had this problem during my dry run yesterday where like you have to take this and store it as Quadgram and then upper it because the plain text is going to be, it should be lowercase. So this will be a lowercase a. But if the whole thing is lowercase, it's not going to find it in potentially in our quadgrams. So we'll just save it as quadgrams and then upper it. And so then we look, everything else stays the same. But now we have to say if quadgram is in quad frequencies, then do this. Oops, got rid of it. Else, probability is just going to equal our worst case scenario that we have here. And the law of probability and the fitness remain the same. So this all looks fine right now. If we run it again, so then our plain text has this score, and what is the worst case scenario for this anyway? Print best fitness. So the worst case scenario is negative 6,287.9, and we got negative 20. So, obviously an improvement. So what we want to do now is if the fitness is better than the best fitness, we want to save it as such. And then we want to store our cipher key in something kind of like best fitness, maybe call it like best cipher key or something like that. So let's get rid of this and we'll do up here Also do best cipher key. So for each of these, then underneath, if fitness is better than best fitness, then best fitness equals fitness, and then best cipher key equals cipher key. And then we also need to take whatever our cipher key is and then save that as best cipher key. So this is just saying like, okay, we have some cipher key that we're currently using that we just made up, and we want to save it because it's better than our currently available best cipher key, which is nothing. We don't have one. And honestly, maybe this can be changed the same way that this is finding the worst case scenario. Our first cipher key is going to be our best just because we don't have anything else. But then this kind of makes this is necessary for, we're going to put all of this in a loop. So this is necessary for the loop. It's not necessary right now. But then we also have to save our whatever our best cipher key into our cipher key is, because the way this algorithm works is we're just like slightly tweaking our best one, and so that we get better results. So if it's not better, like our current cipher key, after we tweak it, if it's not better than our best, we want to just go back to the best and tweak that one and see if we can make that one better. So we can get rid of this log probability. We don't need that, and this should not have gotten this far down anyway. So we're done with this. Honestly, on this line, and yeah, we don't need the text anymore. Okay, so we want to save two characters, so character 1 and then the index. It's going to be equal to random dot choice. Oops, not choice. Choice will return one of the characters, but we want the index since we're doing a swap. So we can do 0 to 25. Then the same thing for character 2. And they might, there's a chance that they end up being the same. That's fine. And we also need a temp. So temp is just going to be equal to whatever our cipher key at character 1 index is. And then to do the swap, we're just going to do our cipher text. Oh, wait, no. To do the swap, we need our cipher key equal to cipher key from 0 to character 1 index. And that isn't inclusive, so it goes everything except whatever letter is at character 1 index. And then we're going to do cipher key at C2 index. So this will be the substitution. And then cipher key at the character 1 index plus 1 to the end. We can actually get rid of this 0. Then we want to do it again. So cipher key is going to be equal to cipher. I think we can copy this, honestly. So everything up to character 2, but not including it. And now character 1 has the index for character 1 has the letter that was at character 2. So instead, we can just do temp since that's stored, and then change this to character 2. So now we have a new cipher key. We need to go back to the top of this fitness and try it again. So the book is just, or not the book, but the article, mentions that this is a hill climbing algorithm. And basically what that means is that say you have a series of hills, and you're comparing uh, just like just an area around a point to see if it's higher or lower uh, than the points around it. Maybe it's lower, maybe it's higher, and you keep going higher, like what we're doing of trying to find, the higher and like highest and highest point. And eventually you will find a high point, but you can't guarantee that that point is the highest point. It depends on where you start uh, in, your search. And so like this algorithm in particular, depending on what that seed is, what that first cipher key is, you will get a um, like a cipher key that like uh, that will be considered the best for that run, but it might not be the best overall. So you have to run it a couple times actually, and um, the author said because of this, maybe just run it like some number like 1,000. I'm just gonna run it like 2,000. Do this loop 2,000 times. So for index, or something like for iteration in range of 2,000. We're just gonna do this over and over of this should actually be above this. So yeah, we actually need it here. And get rid of best fitness. Okay, so we're just going to keep iterating over and over, have our plain text, try to decipher it, and then calculate the fitness. If it's better, then we save that. We'll also just print out a statement. So current best plain text is, then print the plain text is plain text with key, and then we can do our cipher key. So our cipher key, then I think that's everything that we need. So we can try this out. We'll get the one that was used. Not enough arguments for format string. What is that about? Try it again. Hopefully that helped. So we kind of get a little bit like I said, you have to run it a couple times because it might not, the first time might not be the best. So it translates to, I think it's in this one. This simple substitution cipher is a cipher that has been in use for many hundreds of years, blah, 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 right? So we get a little bit like this, and the substitution gets through some of cipher, it looks like if you compare, let me just highlight it. This is the current best key that they have. So XZK, XZT, the J and the W, UM got through, and the O. Oh wait, the M didn't get through. So yeah, this is why you have to run it a couple times, because the first time just might not be the best. Let's run it again. I actually got it one time where I think like only a couple letters were off. So that one wasn't a good starting. That one wasn't the greatest. Let's see how close we can get. So now we get, oh wait, is it this simple substitution? No, it's the simple substitution. So the simple substitution cipher is a cipher that has been in use for many hundreds of years. It basically consists of substituting. This one got really close. I wonder how. So if we copy this, so we got xz. We just we get xztjwumobe, and then y didn't come through. ariqk, p didn't come through. l fsch, then the y obviously, like we said, didn't come through. So that v didn't come through, and then gn, and then d. So this is actually pretty good. If you think about it, this makes sense, right? You would need a pretty big, um, pretty big ciphertext for certain, excuse me, certain letters to match. So for example, if we look at the frequency, what am I on? Like letter frequency, and then okay. So E occurs 11% of the time, which would suggest in like ciphertext of 100 characters, right? E would be 11 of those characters, T would be 9 of those characters, but certain characters like uh, V, J, X, Q, and Z occur less than 1% of the time. So for them to even stand out, for say a V to stand out, you would need like 1,000 characters potentially, and it would show up once. Um, and then the same for, or not once, but about 10 times. But like this one will be about once, about once, about once, about once. So depending on the size, certain characters are going to get jumbled up just because like they don't appear as often. And if you look, this would be which one? E Z T J W M O B E P. P is the first one that's off. So A, B, C, D, E, F, G, H, I, J, K. And if we look, K is only right above V. So it's easy for like to get a coherent plain text, but not have the correct cipher key, only because some letters just don't appear that often. And then that's really the video. I'm super excited that I think the first time I did it, the reason I said it didn't really work that well is because I forgot to set cipher key back to best cipher key. So what was happening is that the cipher key was getting tweaked, but it might not be the best cipher key that was getting tweaked. It was just whatever the current one was. So even though I had this part where I was saving the fitness and the best cipher key, because I wasn't tweaking the best cipher key, just any cipher key was getting tweaked, and it might not have been the best. It could have been the worst. Um, and this 2,000 kind of arbitrary. Maybe if we went to 3,000 or 4,000 or something like that, we would get the correct cipher key. Maybe not. Like I said in the last video, it would take 900 million universes to track every single cipher key if we could check one per second. So over the lifespan of our universe, and that's just kind of crazy. So, but I'm glad that I was able to figure out that this was the one line that was missing, and because of that, it's working as intended. So if you enjoyed, I'm glad. You know, um, frequency analysis is just really cool to me, just because it's like the first big breakthrough in taking away the dominance of monoalphabetic substitution ciphers. And then because of that, the world had to transition to other means, including polyalphabetic substitution ciphers, which would be the next Cipher Saturday video, which is the Vigenère cipher. So if you have any questions, feel free to reach out, or if you have a better way of doing this, feel free to drop a gist in the comments or whatever. And I hope you guys have a great Saturday. Thanks.